of 1.5 ampere. Both values belong to the emitter collector line of the transistor. The first test circuit consists of 3 digital multimeters, 3 potentiometers and 2 constant resistors, plus, of course, the transistor. A lead-acid battery with a nominal voltage of 12 volts is used as a voltage source. The detected voltage of 12.38 volts is considered to be constant during the whole series of measurements. The emitter pin is connected to the negative terminal. The collector is connected to the positive terminal via a constant resistor of 390 ohm. A voltage divider is formed by 3 potentiometers and 1 constant resistor of 1 kiloohm, so that a variable voltage can be attached to the base pin of the transistor. A resistor of 10, respectively 100 ohm is soldered in parallel to the 2 upper potentiometers. The bottom potentiometer is used for the rough adjustment and the 2 upper potentiometers facilitate a fine-tuning of the voltage divider. 1 voltmeter is used to measure the voltage drop between ground and base pin. The other one detects the voltage drop at the resistor between the collector pin and the positive terminal, which is called load resistor. It detects the current running through the base pin. The current running through the collector can be calculated with the help of the measured voltage drop at the load resistor by using Ohm's law. The collector current results in the voltage drop at the load resistor divided by the resistance value. The voltage drop at the collector can also be detected indirectly. The collector voltage results from the battery voltage minus the voltage drop at the load resistor. Let's start the measurement series by turning all 3 potentiometers to their minimum value. We would now expect a base voltage of 0 volts, but 0.013 volts can be detected. The residual resistance of the potentiometers is one explanation of the detected voltage drop. Another one is given by the electrical properties of a transistor, which will be discovered in course of this video. No current through the base pin can be detected and the voltage drop at the load resistor is 0. By turning the bottom potentiometer slightly, a current of approximately half a milliampere is running through the base pin and almost all of the battery voltage is detected at the load resistor. A greater angle of rotation is required to get the same effect while using the middle potentiometer, and even the full turn of the top potentiometer is not sufficient to cause those base current. By adjusting the 3 potentiometers, the base voltage can be varied in small steps. With the help of this simple arrangement, we can record some values. The recording stops as soon as all 3 potentiometers have reached their maximum resistance value. Let's have a closer look at the data. While looking at the curve progression of the correlation between current and voltage at the base pin, you might recognize that it is very similar to those of a semiconductor diode, which was treated at one of the previous videos. Below 0.7 volts, the current running through the base pin is very low. Altering the base voltage at this area of the curve causes just a low variation of the current. Above 0.7 volts, the gradient increases significantly. Altering the base voltage at this area of the curve causes a great variation of the current. There is indeed one single PN junction between the base layer and the emitter of a transistor, which is switched to forward polarity, as we saw at the video about the simulation of a bipolar junction transistor. Thus, the curve progression is caused by those PN junction. The voltage drop at the load resistor is also altering clearly during the series of measurement. while varying the base voltage between 0 and 0.7 volts, the voltage drop at the load resistor increases from 0 to 12 volts. Almost the whole battery voltage drops at the load resistor at this point of the measurement. Thus, there is no more change in the voltage drop at the load resistor while increasing the base voltage above 0.7 volts. The maximum base voltage of this measurement setup is reached as soon as all three potentiometers are adjusted to their maximum value. The resistance of the transistor's emitter collector line can be calculated to be able to plot those values in relation to the base voltage. All we need to know is the resistance value of the load resistor, the voltage drop at this device, and the battery voltage. The relation between the voltage output of the battery and the voltage drop at the load resistor equals the relation between the total resistance and the resistance of the load resistor. Furthermore, the total resistance equals the sum of the value of the load resistor and those of the emitter collector line. The resistance of the transistor can be calculated by using those two equations. As you can see, the resistance is altering clearly between 0.6 and 0.7 volts. That's why transistors are called adjustable resistors. We can't get suitable values at the range between 0 and 0.6 volt by using this measurement setup, because of the fact that the resistance value of the emitter collector line altered during the measurement series. The voltage drop at the emitter collector line was altered too. To get reproducible values, the voltage drop at the collector has to be kept at a constant level, while the curve progression of voltage versus current is recorded at the base pin. By using the knowledge series, we can build a better test circuit. The load resistor is replaced by a PNP transistor. Thus, we get a voltage divider consisting of two adjustable resistors, by what we can align a constant voltage drop at the NPN transistor. The resistance of the NPN transistor is adjusted by attaching a positive voltage drop at the base pin, like we did at the first measurement series. In contrast, the resistance of the PNP transistor is adjusted by attaching a negative voltage drop between emitter and base pin. To limit the current running through the voltage divider, there is a filament lamp connected in series to the transistors. The functionality of the second filament lamp will be treated at the video about adjustable voltage sources. 4 digital multimeters are used to measure the voltage drop and the current at the base and the collector pin of the NPN transistor. As we saw at the first series of measurement, even a current below 1 microampere affects the electrical properties of the transistor clearly. Hence, the current running through the base pin is recorded indirectly by measuring the voltage drop at a 1 kΩ resistor. Potentiometers with a value of 1 megaohm, respectively 100 and 10 kΩ, are used to adjust the voltage drop at the base pins of the two transistors. Let's record the relation between voltage and current at the base pin with a constant voltage drop of 5 volts at the collector pin by using this arrangement. After adjusting a certain voltage drop at the base pin, the voltage drop at the collector pin has to be readjusted to 5 volts. As you can see, those voltage is increasing slowly, making it hard to adjust a constant voltage with the help of the PNP transistor. This is caused by the heating of the filament lamps and the transistors, by what the resistance of those devices is altering. After some time has passed by, the state of thermal equilibrium is reached, and we can start the series of measurement. The test series is repeated with a collector voltage of 2, respectively 7 volts. Once again we get the typical curve progression of a forward biased PN junction. The higher the collector voltage, the higher the current running through the base pin becomes while looking at points of equal base voltage. The electric field of the collector voltage is pointing into the same direction as those of the base voltage. Let's have a look at the relation between base current and collector current, which can be determined with the recorded values too. We can see an almost linear correlation between both values, hence the collector current is approximately beta times the base current. The non-dimensional parameter beta marks the slope of the curve, which equals the current gain. Beta is increasing slightly with an increasing collector voltage. With the values recorded for the BD135, we get a current gain of approximately 130. While recording the curve progression of current versus voltage at the transistor's collector pin, the current running through the base pin has to be kept at a constant level. Hypothetically speaking, we could also keep the base voltage at a constant level, but when looking at the datasheets of transistors, there's predominantly a constant base current given for the plots. 3 test series are recorded using a constant base current of 50, 100 and 200 microampere, which correlates to a voltage drop of 50, 100, respectively 200 mV at the 1 kΩ resistor. Between 0 and approximately 1 volt, the current running through the collector pin is increasing significantly, but the measurement setup doesn't facilitate the observation of this area accurately. Besides some exceptional cases, transistors are not operating at these low voltages, hence we will not have a closer look at this area of the curve. Above 1 volt there is an almost linear correlation between voltage and current. The higher the base current, the higher the collector current becomes, meaning the resistance is decreasing with increasing base current. In contrast, the resistance of the emitter collector line is increasing with increasing collector voltage. Those effect decreases with an increasing base current, meaning the slope of the curve is rising above 1 volt the higher the base current becomes. By drawing the resistance of the emitter collector line versus the base voltage at a constant collector voltage of 5 volts, we can see that the resistance is altering from 1 megaohm down to just 59 ohm. The variation of resistance is used to amplify signals with the help of transistors. The circuit running through the base pin is called input circuit, and those running through the collector is called output circuit. Hence, the current voltage curve of the base is called input characteristic, and those of the collector is called output characteristic. The relation between the base current and the collector current of a transistor is called transfer characteristic. The values recorded at the previous measuring series include the relation between collector voltage and base voltage at a constant base current. We get the following curve progression. While the collector voltage is increasing, a lower base voltage is sufficient to keep the base current on its constant level. Like mentioned before, both electric fields are pointing into the same direction, hence the increasing collector voltage causes a higher base current if the base voltage would be kept on a constant level. The curve progressions of input, output, transfer and reaction characteristic are often plotted in a 4-quadrant family. By interchanging the connections of emitter and collector pin, we can determine that bipolar junction transistors are not built symmetrically. The PN junction between base and emitter differs from those between base and collector. This arrangement is called reverse mode. While increasing the voltage at the emitter-collector line without a base voltage attached to the transistor, the device becomes conductive near a voltage of approximately 8 volts. A current of approximately 20 mA is running through the emitter of the transistor. Also, a base current of 20 mA can be recognized, which is running contrary to the normal direction. In reverse mode, the maximum voltage of the reverse biased emitter base junction is just some volts. So let's record the current voltage characteristics of the base pin at an emitter collector voltage of 5 volts. The resulting input curve demonstrates that the electric properties are altering clearly while interchanging the emitter and collector pin. The current gain is considerably lower and the curve progression is less linear. The dopant concentration of the layers and the transistor's internal structure is usually optimized for forward mode operation. By using a 2-channel oscilloscope operating in XY mode, the curve progression of a transistor can be recorded quickly. One channel is used to measure the voltage drop at the base pin, the other one to measure the current running through the device. Once more, the base current is recorded indirectly by measuring the voltage drop at a series resistor. A battery supplying a constant voltage is connected to the output circuit of the transistor. An AC transformer is connected to the transistor's input circuit. Like already explained at this video, the collector voltage is not kept constant while using this simple measurement arrangement, hence we won't get reproducible values. There is another video about recording curve progressions with the help of an oscilloscope. The displayed curve is similar to those of a forward biased semiconductor diode. Note that the curve is drawn mirror inverted, hence the base voltage is increasing from the right to the left of the x-axis. With the help of this arrangement, I would like to demonstrate the influence of temperature on the recorded values. The transistor is heated up by a fan heater, by what the curve is moving to the right. In comparison to the cold transistor, a clearly higher base current is running through the device if the base voltage is kept at a constant level. While cooling down, the curve is moving slowly to the left. So if you intend to do very precise measurements, you have to ensure that the temperature of the transistor is kept at a constant level. Finally, I would like to demonstrate that the limit values of a transistor have to be considered while using those devices. I am now using a BC808, whose limit values are lower than those of the BD135. This arrangement is used to generate a critical base current. The maximum value given by the manufacturer is 100 mA. A higher current is tolerable just for a short span of time. As you can see, the LED light can still be switched by the transistor. If the base current gets too high, the device gets destroyed inevitably. Another value to be considered is the maximum collector current, which is 500 mA for the BC808. Here you can see an electric motor being switched with the help of the transistor. But you should prevent the motor from getting blocked. Now a very high current is running through the transistor, which is why the device is heating up strongly, leading to the melting of the solder. After resoldering the collector pin, you can see that the transistor has been destroyed by the high current. Even though there is no voltage applied to the base pin, a current is running through the emitter collector line. The third method to destroy a transistor by ignoring the limit values is demonstrated by this arrangement. The BD135 is used to dim a filament lamp. With the adjusted base current of nearly 44mA, we can detect a collector current of approximately 1A and a voltage drop of 6V at the device. Hence, 6W of electric power are turned into heat by the transistor. As you can see, the device is heating up quickly, and after some seconds a match can be fired at the transistor. Sooner or later the transistor will be destroyed. The maximum heat dissipation of the BD135 is 12.5W according to the datasheet. The transistor has to be equipped with a heatsink to be able to dissipate those high electric power. The maximum power dissipation of transistors is marked by a line at the output characteristic. The maximum voltage and the maximum current are also marked. Operating a transistor at a too high collector voltage also leads to unwanted effects, as we could see while recording the values in reverse mode. The recorded values of this video are available at the project page. That's all about the electric properties of bipolar junction transistors for now. Thanks for watching.